Good morning. Today is going to be ionic bonding. We're going to talk about an introduction to ionic bonds, what it is, where we see it in everyday life, and how to represent ionic bonding through Lewis dot diagrams and naming. So let's get started. First, I want to review what we did earlier in the week. We talked about the ionic forms of different atoms. And we talked about the octet rule, so the tendency for atoms to want to be stable by acquiring a full valence shell. We also talked about anions and cations, so atoms that tend to become negative because they gain electrons, they're called anions, and chlorine is known to become an anion. And atoms that tend to be positive because they lose electrons are cations. So here we have two atoms. Sodium is known to become positive and chlorine is known to become negative when they become ions. And the reason being is because atoms like to have a full valence shell. So we like to follow the octet rule. Atoms are really only stable, they're really only happy when they have a complete valence shell. Well, if we look at sodium, and let's go down to our little periodic table here. So sodium's in the third period and the first group. So sodium has one valence electron, and that's it right here. But in order to have a full valence shell, sodium is in the third period, so it has 3 shells. And we know that our filling order is the first shell can hold 2 electrons. And we see that here. There's only 2 electrons in the very first shell in both atoms. And then the second shell can hold 8 electrons. And we see that up here, both atoms have 8 electrons in their second shell. And the third shell can also have 8 electrons. So both atoms have a full first shell, a full second shell, and then on their third shells, we could have a total of 8, but sodium only has 1. So it's 7 away. It's 7 electrons away from having a full valence shell. That's a ways away. And that's a lot of work to gain 7 electrons. Chlorine, on the other hand, has 1, 2, 3, 4, 5, 6, 7. It's already got 7 valence electrons. So in order to get a full valence shell, in order to get an octet of 8, all it has to do is gain 1 electron. It just needs 1 extra electron, which is far more feasible than the 7 electrons that sodium would need to gain in order to have a full outer valence third shell. So what is sodium going to do? It can't gain 7 electrons. It's too much work. So its solution to the problem is not to gain electrons, but actually to lose electrons. And all it would have to do is lose this 1 electron on its outer shell, and that whole shell is gone. It wouldn't exist anymore. It doesn't have any more electrons on it. There's no more electrons at that energy level. So its valence shell then becomes the shell underneath. And the shell underneath has 8 electrons. It is a complete shell. So sodium is stable, sodium is happy, and it can move on with its day as an ion. And because it's lost an electron, sodium normally has, so it's sodium here, so we have it's the 11th atom, so it's an atomic number of 11, so it's got 11 protons. So if it has 11 protons in its neutral form, it would have 11 protons and 11 electrons, but because it's lost an electron, it doesn't have 11 anymore, it has 10. And if it has 11 protons and 10 electrons, well, it has a positive charge of 11, a negative charge of 10, and so 10 positive charges cancel out 10 of these negative charges, but there's 1 positive charge left over. And so its net charge would be +1. So we're going to write a positive 1 here, right here, 1 plus. Chlorine, on the other hand, would need to lose 7 electrons to work the way that sodium does, and it's a lot easier for chlorine just to gain 1 electron than to lose 7. So it's going to gain 1 electron, and it's going to get it from another atom. So it's going to add an electron to its outer valence shell from another atom, and it's going to have a full octet or a full valence shell with 8 electrons, but now it's an ion, and its net charge, because it's gained an electron, is -1, because it has 1 extra electron than it does proton, because normally in its neutral form it has the same number of electrons as protons. And chlorine being the 17th atom on the periodic table, we would normally have 17 protons and 17 electrons, but because we've gained an electron, we now actually have 18. So it has a net charge of -1. Now, chlorine likes to gain its electrons from another atom, and sodium likes to lose electrons, but it will lose electrons to another atom. So what we see between atoms is the atoms that we like to consider electron givers, which tend to be these electrons on, or these atoms on the left side. So all these atoms here in group 1 and 2, they either need, and actually I won't highlight hydrogen because it doesn't really count. It's an exception. But if we highlight all of these atoms in group 1 and 2, they want a full valence shell. And for both these groups, it's easier for them to lose the few electrons they have on their valence shell than to try to work at gaining a total of 8. All of these group 2 atoms would have to gain 6 electrons to get a full valence shell, and all of these atoms in group 1 would have to gain 7 electrons to get a full valence shell, and that's just not feasible. So what they do instead is they lose their electrons by giving them to other atoms. And then they're left with the full valence shell underneath. So these we'll call electron givers, or atoms that tend to become cations, because they tend to become positive because they're giving away 1 or 2 of their negative charges. And then all of the atoms on this right side we'll call electron takers, or anions, because they tend to take electrons from other atoms and gaining a net negative charge. So we have all these electron givers on the left side and all these electron takers on the right side. Well, it just makes sense that these electron givers and these electron takers would bond together, because they make this beautiful relationship where they like to give their electrons away and they like to take the electrons. So these group 1 and group 2 atoms will give their electrons to these group 16 and group 17 atoms. And so if we look at the entirety of the periodic table, the more left we go on the periodic table, the stronger the electron givers. So the more likely the atoms are to give away their electrons. And the more right we go on the periodic table, with the exception of the halogen, or the noble gases rather, with the exception of the noble gases, and we'll talk about that in a moment, but the more right we go on the periodic table, the more likely atoms are to be electron takers. So when we talk about ionic bonds are between metals, which are the electron givers, so these metals over here, and nonmetals, which are these atoms over here. So ionic bonding is between metals and nonmetals, because metals are electron givers, they're the cations, And nonmetals are the electron takers. They're anions. All right, so let's explore this in a little more detail. But first, let's talk about naming conventions of ions. For some reason, when an atom or an element becomes negatively charged, we like to change the name. So when something becomes a negative ion, and it doesn't count for positive ions, so it's not going to count for these metals over here. It's only going to count for these nonmetals over here, the electron takers. When the atoms gain an electron, we change their name a little bit. And it's so small, it's almost silly, but let's take fluorine, for example. This is its base name, this is its periodic table name, but when it becomes an ion, when it becomes negative, we get rid of this last suffix of the word, and instead we change it to IDE. So same with chlorine, as soon as it becomes a negative ion, we get rid of this INE and we turn it into IDE. So instead of chlorine, it's chloride. Instead of fluorine, it's fluoride. Instead of bromine, the negative atom is called bromide. Instead of iodine, the negative ion is iodide. Oxygen, oxide, sulfur, sulfide, nitrogen, nitride, hydrogen, and hydride. And that's why when we're talking about salt, which is NaCl, is sodium chloride, we don't say sodium chlorine, we say sodium chloride, because chloride, the chlorine atom, becomes a negative ion in the compound, and so it is now chloride. So this is sodium chloride. Now, the positive ion doesn't change, the cation doesn't change name, it's only the anion that does. Okay. So let's talk a little bit more about bonding. Let's talk about potassium bromide. So potassium, the symbol for potassium is K. We have bromide right over here. So we have 1 valence electron on potassium, and we have 7 on bromine, because it's not an ion yet. So let's draw the Lewis dot diagram. So I have potassium, and I'm just going to draw 1 little valence electron, and then I'm going to draw bromide, and it's got 7. So 1, 2, 3, 4, 5, 6, 7. Now, potassium is an electron giver because it wants to get rid of this last little electron, because otherwise it would have to gain 7 to have a full valence shell. But it has a beautiful valence shell underneath. It has a beautiful full shell underneath, and if it can get rid of this electron here, then all it would have left is 1 valence shell, and then it would be super happy. So it's trying to get rid of this electron. Bromine is looking for an electron. It wants to take an electron, and it only needs 1. It only needs 1 electron to complete this valence shell. So if bromine and potassium are hanging out together, they make this beautiful arrangement where bromine pulls that electron from potassium, because potassium is not holding onto that electron very tightly. It doesn't really want it there. So it's ready to let it go. And bromine really wants that electron. It has very high what we call electronegativity. It really wants to get that electron because it holds onto its electrons very tightly. So this electron of potassium is going to get given and taken by bromine. Now that's not bromine anymore, now it's bromide. So now we have a potassium atom, and I'm going to redraw these Lewis dot diagrams, but I'm going to draw them as ions. So this is going to become a positive charge now because it's got 1 less electron, so it's got a 1 positive charge. We could write the 1 in there, but by convention, just like in mathematics, we don't really write the 1 very often. If it's just a charge of positive 1, we just write a plus. Now, bromine, which is now bromide, has gained an extra electron, so I'm going to draw all its 8 electrons now. And because it has one extra electron than it normally would as a neutral atom, we're going to draw its charge as -1. So now I have this positively charged potassium atom and this negatively charged bromide ion. And they're hanging out together. And we know intuitively that negative and positive charges attract. So as soon as that electron displacement takes place, as soon as that electron transfer takes place, this positive potassium and this negative bromide are now attracted together. They're drawn together by their opposing charges, and they create an ionic bond. We call it ionic bond because it's bonding between two opposite charges. So now this becomes potassium bromide. And we would draw it as a Lewis dot diagram, as some people do this differently. I like to draw the non-metal in brackets, so in these big square brackets, and then I'll draw however many potassiums there are. In this case, there's 1 potassium per bromide ion, and we'll discuss ratios a little later, but I'll draw the potassium right out here. It doesn't matter what side we draw it on, but I'll just show that they're bonded like that. They're bonded because it's positive and negative charges, just like magnets, positive and negative magnets. The stronger the magnet, the harder it is to pull it away. These are very strong charges, +1 and -1, and so they tend to stick together. And what happens is I have this potassium bromide now. 1, 2, 3, 4, 5, 6, 7, 8. And typically, I'm not just going to have one compound of potassium bromide. If there's potassium and bromide together in a solution, there's going to be billions and trillions of potassium and bromide molecules. So they're all going to be hanging out together. And the thing is, this potassium is not just attracted to this bromide, it's attracted to the other compounds around as well. So all of these potassium bromide ionic compounds will come together and join these giant crystal lattices, so these ionic lattices, and it will look something like this. So each one of these purple ones is a visual representation of a potassium ion, and each one of these green ones is a representation of bromide. 1, 2, 3, 4, 5, 6, 7, 8. And they all come together in these giant lattices. And if we take an example of salt, now this is on a much bigger scale, so we're not seeing the individual atoms, but even on a larger scale, we can see the manifestation of these crystals by the particular shape. And this is sodium chloride, which is also known as salt, the salt that we eat, the table salt. If we look at it under a microscope, or even if you look at it using a magnifying glass, you'll see that sodium chloride or salt are these little tiny crystalline cubic grains. And that's a result of this crystalline or this crystal lattice that ionic compounds tend to form. One more thing I need to touch on. You might be asking, okay, well, if potassium has lost its electron and it has a full valence shell underneath now, when I draw the Lewis dot diagram, why aren't I drawing the 8 electrons that are remaining underneath? It's because when we draw Lewis dot diagrams, we only ever draw the valence shell that would exist in the neutral atom. So by showing no electrons, I'm basically telling the reader it's lost its 1 electron and its original valence shell is now empty. We can assume that the inner shell is full because we know how atoms work. This is just demonstrating the fact that it's empty. If we were to draw potassium with 8 electrons now, we would assume that it has gained 7 rather than lost 1. All right. So here's some examples of how to draw ionic compounds using Lewis dot diagrams. So let's do a quick and easy one. Let's do sodium chloride. So sodium is the electron loser, so it gives electrons, so it's going to become a cation, it's going to become positive. Chlorine is the electron taker, so sodium here So it's only got one valence electron, and then chlorine here, it's got 1, 2, 3, 4, 5, 6, 7. So it's ready to go. It's got to take one. So it's going to become, so NaCl, normally sodium would have 1, and normally chlorine would have 7. But we know that chlorine is going to take that one from sodium. Oops, I drew chlorine with 8 rather than 7. So chlorine is going to gain that 8th one, and what we're going to have is chlorine as an ion. So we draw it like this, and it's going to have 8 and a net positive 1 charge, so we'll just write a plus. And I like to put the brackets around the nonmetal, and then sodium has lost an electron, so it's a negatively charged of 1, and so I like to draw it just close. You can draw it on the left side or the right side or below or above. It doesn't really matter where you draw it, as long as you're drawing that 1 right next to the nonmetal. Okay, so here we have iron bromide. Let's not talk about iron bromide yet, because it's one of those, we're getting into the exceptions. Let's do something a little bit easier. Let's see. Let's do calcium chloride. So calcium chloride is going to be CaCl2. Now, this number on the bottom, this is a superscript, or sorry, this is a subscript. This number that's immediately to the right of the atom indicates how many there are of that atom per calcium. So for every 1 calcium, there's 2 chloride ions. So I'm going to draw our chloride ions here, and I need to draw 2 of them. Now, normally chlorine would have 1, 2, 3, 4, 5, 6, 7 outer electrons in this valence shell, and then calcium has 2, 1, 2, so it's 2. So calcium wants to lose 2, and chlorine wants to gain 1. So here we're going to have 7, and it's going to gain 1 to become 8. And then we have another chlorine, so this is going to become a negative 1 charge, so negative. And I like to put my brackets around the nonmetals. And then we have another one here, and so chlorine 1, 2, 3, 4, 5, 6, 7, but it's going to gain 1 like that. And where did it get those 2? Well, it got those 2 from calcium, because calcium normally has 2 valence electrons. And so it has 2 to give away. So it's going to give 1 away to that chlorine, and it's going to give 1 away to that chlorine. And because it's got 2 to give away, once it's lost those 2, its ion will become not just 1 plus, it's lost 2 negative charges. So it's going to become a positive 2 charge. And I'm just going to draw it right down here, right below my chloride ions. And I forgot to draw my negative sign here. All right, let's talk about naming. So this should be a subscript, so this should be K2O, and this is lithium fluoride, and this is potassium oxide. So all we have to do when naming ionic compounds is look at what element is in the first and what element is in the second part of the compound, and we always write them. This is the chemical formula. This is the chemical formula, and we always write the chemical formula and the name metal first, then the nonmetal. So it's always the metal first and then the nonmetal. So this is going to be potassium. Now, that's an oxygen, but we don't call it oxygen because if it's part of an ionic compound, it becomes an ion because it's going to become negatively charged. So it's not oxygen. We get rid of this part and we call it an oxide. So this is going to be potassium oxide. And this is going to become lithium, not fluorine, because fluorine is going to become an ion. It's going to be lithium fluoride. Now, as an extension to this, if you see, these are a bunch of common chemicals. Oh, these are a bunch of common ionic compounds. And if you'll notice, they all bond in a very specific ratio, which means when they create these crystalline lattices, the ratios are different. When we talked about sodium chloride or potassium bromide bonds 1 to 1. So there's 1 potassium for every 1 bromide. And we can see that in the crystal lattice. For every 1 potassium, there's 1 bromide. So the ratio is 1 potassium to every 1 bromine ion. But that's not always the case. And in fact, even here, we looked at an example where that wasn't the case, calcium chloride. There's 2 chlorides for every 1 calcium. So if we were to draw that crystalline lattice, we would have to draw 2 chlorines for every 1 calcium. And we would have to build an entire crystalline lattice using that ratio. So 1 calcium for every 2 chlorine atoms. And if we look down here, all the ratios are indicated by these little subscripts. That subscript is to the right of potassium, so that means there's 2 potassiums for every 1 oxygen. Or here there's 2 iodines or iodides for every 1 magnesium, 3 chlorides for every 1 aluminum, so on and so forth. So my question for you as an extension is, and we discussed it briefly when we talked about calcium chloride, is how do you predict the ratio of an ionic compound? And here's an example. Here's chlorine, which is a -1 ion because it likes to gain an electron. And here's magnesium ion, which is a +2 ion because it likes to lose 2 electrons to get a full valence shell. How can you predict what the ratio would be? In other words, how can we write the equation? Remember, metal first, then non-metal. And then what would we determine to be in the subscripts? If the subscript is 1, we don't write the 1. For example, this would be K2O1 because there's 1 oxygen, but just like in mathematics, if it's just a 1, we don't write it in, we just assume that it's there. And that's it. If you can do this, awesome. This is something that you will cover in grade 10. It's typically something we would cover in grade 9, but because of this disruption, we're not going to get into it because we need to get into physics before we get into space, and we only have about a month and a half for that. So if you have any more questions, let me know. And I'm going to do another lesson tomorrow and tutorials on Thursday. Have a great day, everybody.